Hi everyone, welcome to Mathly. Today we are diving into Principal Component Analysis or PCA, a powerful tool in machine learning and data science. Whether you're working with complex datasets in finance, genetics, or image processing, PCA helps simplify data while retaining meaningful insights. High-dimensional datasets can be difficult to interpret or visualize. Instead of analyzing hundreds of features separately, PCA restructures the data, capturing the most important patterns in a more compact form. But how does PCA achieve this? It finds new axes called principal components that highlight the strongest variations in the data, making it easier to work with. The best part? I will guide you through implementing PCA step by step using orange data mining. Let's get started. Imagine you have a huge stack of books, each filled with different types of information. Instead of reading every single page, what if you could summarize the key points from each book while keeping the most important details? That is exactly what principal component analysis does for the data. PCA is a powerful dimensionality reduction technique used in machine learning and data analysis. When working with large datasets with many variables, it can be challenging to interpret or visualize the data. PCA helps by transforming the data into a smaller set of key features called principal components while preserving as much information as possible. It does this by finding new axes that best represent the variation in the dataset. Instead of manually selecting features, PCA automatically identifies patterns and compresses data without losing critical insights. PCA is widely used in image processing, finance, genomics, and even facial recognition. Now, let's explore how PCA works and how we can apply it using orange data mining. Principal component analysis is a powerful technique that simplifies large datasets while preserving the most essential patterns. Let's break down how it works step by step. Step 1. Identifying variability in the data. Imagine you have a dataset with multiple features like height, weight, and age. Some of these features may be more important than others when analyzing patterns. PCA identifies the directions or principal components that capture the most variation in the data. Think of a cloud of data points forming an elongated oval shape. PCA finds the axis along which this spread is the largest, that is, the first principal component or PC1. The second principal component or PC2 captures the next highest variance and so on. If we extend this to 3 dimensions, a 3D plot would show PC1, PC2, and PC3, illustrating how PCA progressively captures the most significant patterns in the data while reducing complexity. PCA starts by standardizing the data to ensure all features are treated equally. It then calculates the covariance matrix to measure how different features relate to each other. The covariance matrix is an essential component in PCA because it measures how different features of the dataset relate to each other. Essentially, covariance tells us whether two variables tend to increase or decrease together. In the context of PCA, the covariance matrix helps us understand the relationships between the features, allowing us to identify patterns and correlations in the data. Once the principal components are identified using the eigenvalues and eigenvectors, PCA sorts them in descending order based on the eigenvalues. The larger the eigenvalue, the more variance that principal component explains in the data. By ranking the principal components in this way, PCA ensures that the components with the highest variance are prioritized. This allows for effective dimensionality reduction where the most important components or those explaining the most variance are kept, while less significant components can be discarded, simplifying the dataset while retaining its key features. Step 2. Transforming data into principal components. Instead of using the original variables, PCA rotates the dataset to align with the newly found principal components. These components help reduce redundancy while keeping critical information intact. The first principal component, or PC1, captures the highest variance in the dataset. The second principal component, or PC2, is perpendicular to PC1 and captures the next most significant variation, and so on. This transformation allows us to represent high-dimensional data in a lower dimensional space without losing much information. Step 3. Reducing dimensions while preserving information. Once the principal components are identified, we can choose how many to keep based on how much information or variance they retain. Instead of using all original features, PCA enables us to work with just a few principal components, significantly simplifying the dataset. For example, high-dimensional data such as 100 features can be reduced to just a few principal components, making analysis and visualizations much easier. PCA is commonly used in image compression, finance, and gene expression analysis, where reducing complexity improves efficiency without major information loss. Let's consider the example of PCA in stock market analysis. Imagine you're an investor analyzing hundreds of different stocks. Each stock has multiple attributes: price, trading volume, market capitalization, and more. Tracking all these variables can be overwhelming. PCA helps simplify the analysis while preserving key trends. Step 1. Collecting stock market data. A dataset contains daily price movements, volatility, and other financial indicators for hundreds of stocks. Some of these variables are correlated. For example, stocks in the same industry tend to move together. Step 2. Applying PCA to identify key patterns. PCA analyzes which factors influence the stock movements the most. Instead of looking at hundreds of individual stock prices, PCA finds a few principal components that represent market trends. For example, PC1 might represent the overall market trend, whether the market is going up or down. PC2 might capture sector-specific movements, such as tech stocks versus healthcare stocks. By focusing on just few principal components instead of analyzing every stock separately, investors can spot trends faster and make more informed decisions. Step 3. Using PCA for portfolio optimization. Investors can use PCA to reduce risk by selecting stocks that behave differently, which are uncorrelated stocks. Instead of manually picking stocks, they can use principal components to group stocks into diversified portfolios. Now that we understand how PCA simplifies stock market analysis, let's see it in action using Orange data mining. Now, let's take a look at how we have set up our workflow in Orange data mining to perform PCA on the Zoo dataset. First, I have added the Datasets widget and loaded the Zoo dataset, which contains different animals and their characteristics, such as whether they have hair, feathers, whether they lay eggs or produce milk. Next, I have connected the Data Table widget to inspect the dataset. Here, we can see the names of the animals, their types, such as mammals, fish, or birds, and various attributes that define them. The dataset contains 100 instances with 16 features. So now I have connected the dataset to PCA widget, and this is how it looks like. This graph in the PCA widget visualizes the variance explained by principal components. Here's what each part represents. The x-axis, or the principal components, represents the number of principal components, or PCs, used to describe the data. The y-axis, or the proportion of variance, shows the amount of variance each principal component captures. Now, let's take a look at the lines in the graph. The red line, or the component variance, represents the variance explained by each individual principal component. The first PC explains the most variance, and the subsequent PCs explain progressively less. The green line, or the cumulative variance, represents the total variance captured by adding up the principal components. You can retain 90% of the variance in the initial data by just picking 11 out of 20 principal components, and 98% of initial variance by picking 15 out of 20 components. This means that using the first two principal components captures nearly half, that is 47.6% of the information in the dataset. What are the key takeaways from this? The first two PCs capture nearly half of the dataset's variance, meaning they retain a good amount of information. Using more PCs would capture additional variance, but each additional component contributes less variance. In many cases, choosing the top few PCs that explain most of the variance is enough for dimensionality reduction without losing too much information. Once PCA is applied to the dataset, the data table connected to the PCA widget displays a transformed version of the original data. The key difference here is the presence of two new columns, PC1 and PC2. PC1 or Principal Component 1. This represents the direction of maximum variance in the dataset. It is a new feature created by PCA that captures the most important patterns in the data. PC2 or Principal Component 2. This is the second principal component and captures the next most significant variance after PC1. It is uncorrelated with PC1, or it is orthogonal to PC1 in the transformed space. PC2, when combined with PC1, explains 47.6% of the dataset's total variance. Why do we need these new features? Instead of using all original features, we now have PC1 and PC2 which serve as compressed representations of the data. These new features help reduce dimensionality while retaining the most crucial information. PC1 and PC2 are used in the scatter plot widget to visualize how the data is distributed in the new transformed space. To explore the results, I have connected the PCA to a scatter plot widget. This allows us to see how animals are grouped based on principal components, setting principal component 1 on the x-axis and principal component 2 on the y-axis. Additionally, we color the points based on animal types, which helps us visually identify patterns and relationships within the data. Here, mammals are grouped together. This suggests that mammals share common characteristics that are strongly represented in the first two principal components. Features like body temperature regulation, live birth, and fur or hair might contribute to their separation from other animal types. Mixing of insects, birds, and invertebrates. The overlap between these groups indicates that some features are shared among them, making their distinction less clear in the first two principal components. Since PCA reduces high-dimensional data to just a few principal components, some loss of information is inevitable. This can lead to groups appearing mixed if their differences lie in components beyond PC1 and PC2. To get a clearer separation, additional components like PC3 or PC4 might need to be explored. Let's take a closer look at one of the clusters in the scatter plot by selecting 4 points from it. After making the selection, we can observe that the data table widget displays 6 records instead of 4. This happens because some animals share the same PC1 and PC2 values, meaning they were projected to the exact same position in the transformed space. Looking at the data table, we can see the feature values of these animals. Many of them have similar characteristics, such as not having hair, laying eggs, or being airborne. This similarity in their original attributes is what caused PCA to assign them the same transformed coordinates. Since PCA reduces the dimensionality while preserving variance, animals with closely related features may end up overlapping in the scatter plot, forming a compact cluster. This highlights how PCA captures underlying similarities in the dataset. Even though the animals may differ in specific attributes, they are still grouped together because their overall patterns align in the principal component space. In conclusion, our orange workflow allowed us to explore and analyze patterns in the dataset using principal component analysis and scatter plots. We observed how different animals are grouped together based on similar traits, with some clustering due to identical PC1 and PC2 values. This clustering helps us understand which features were most influential in differentiating the animals. Now, let's explore some real-world applications of principal component analysis. Image compression and facial recognition. Ever wondered how social media platforms store millions of images efficiently? PCA is widely used in image compression. It reduces the amount of data needed to represent an image by extracting the most important features. In facial recognition, PCA helps identify key facial features, allowing systems to recognize faces with minimal data storage. Medical diagnosis and genomics. In medical research, PCA is used to analyze complex genetic data. For example, in cancer research, doctors analyze thousands of gene expressions at once. PCA helps identify patterns that differentiate between cancerous and non-cancerous samples, improving early detection and treatment. Stock market analysis. Financial analysts deal with large amounts of stock data, including price trends, volatility, and trading volume. PCA reduces this high-dimensional data by finding principal components that capture the most significant market movements. This helps in trend prediction and portfolio optimization. Speech and audio processing. Voice assistants like Siri and Google Assistant rely on PCA to process speech data efficiently. It helps remove background noise and extract essential features from audio signals, making speech recognition more accurate and efficient. Customer segmentation and marketing. Companies use PCA to analyze customer behavior and group them into different categories. By identifying key purchasing patterns, businesses can tailor their marketing strategies, improve product recommendations, and enhance customer experiences. And that is how you can use orange data mining to apply principal component analysis in real-world scenarios. We explored how PCA helps reduce dimensionality, identify key patterns in data, and its applications in fields like image processing, healthcare, finance, and speech recognition. If you found this video helpful, don't forget to like, share, and subscribe to Mathemly for more data science tutorials. Comment below with what you would like to learn next. Thank you for watching and see you next time.